Hi everyone, welcome to the first paper read of the channel. We're gonna be reviewing the AlphaCode 2 technical report. This was released some weeks ago by Google. Basically, this contains everything related on how they have been implementing this second version of AlphaCode. So when AlphaCode released, it got quite a lot of attention from the community because it was just basically trying to use LLMs that we call today, like large language models for code generation. That was something huge at the time. Nowadays, maybe it isn't that huge because we have all the models, open source models as well, that we can use to generate code. But at the time, it was quite interesting for the community. So it is quite short, to be honest. It doesn't have a lot of stuff. It's just basically a technical report on how they implemented the system, but they provide some details. So as you can see, I'm just sharing my VS Code right now. We're gonna be just trying to implement some of the ideas on this paper so that we can have an open source AlphaCode 2 version of it. It isn't that complex. I've read it before, quick read, to be honest. And as with many papers from Google, it's quite difficult to finish the paper without having that impulse to write the code to try to implement some of the ideas because even though many of them aren't too technical, like these technical reports they don't have a lot of mathematics and it's basically coding, just for you to know how they perform, what they have been implemented behind the scenes. But it has happened to me. Like I was reading this and I was like, I need to stop this. I need just try to hands-on code on everything, and that has happened to me also with Cohere papers, Anthropic papers. Those papers are quite code related, like they provide a lot of ideas, not too many mathematics, so it's something that you kind of have the impulse to write. So AlphaCode 2 technical report. AlphaCode was the first AI system to perform at the level of the medium competitor in competitive programming, difficult reasoning tasks involving advanced mathematics, logic, and computer science. This paper introduces AlphaCode 2, a new enhanced system that massively improved performance powered by Gemini. We don't know a lot of details about Gemini, to be honest. We don't know the parameter count. We don't know if it's a mixture of experts. We don't have a lot of details on how it works. We know that it has been trained from the scratch to be multimodal. I think they do something very similar to NextGPT. I'm just gonna show you guys. So we look for NextGPT. Yeah, I think it is something very similar to this. Like you basically encode images, audio, and video, right as if they were special tokens. This is a very interesting paper to read as well. So I'm just gonna take notes for the next one. If you are looking for paper reads or code implementation or some quick code implementation of these different systems, we can just have a look. So just leave it on the comments. As well, subscribe and like if you like this kind of content. We're just playing around with the things that we are planning for the channel for Diet Academy. Yeah, basically this is quite interesting. So this looks like well, they use, so NextGPT behind the scenes is using image buying. Image buying has, as you can see, this kind of special tokens, right? That kind of image. They say, okay, these things that you're seeing right here, this is where the image starts, this is where the image ends. And they basically, when they generate image as well or audio as well, what they do is they append those special tokens. So it looks like it's trained in a very similar way to this. It's not something like Lava. If you've been reading about Lava, this works in kind of way of the adapter. So basically, what they're doing in here is they are appending information from the image. As far as I know, it doesn't happen right at the beginning. So basically, it's an adapter that is added to the model. I think it's Llama as a layer. So that happens right pretty much at the middle or at the end of the model, more or less at the model. And I don't know a lot of how this is working, but I have read some reports on how Lava kind of kind of is implemented using adapters. So not too many details about it, but I think this thing Lava in here is implemented in a different way on how NextGPT is implemented. So yeah, that is pretty much everything we know about Gemini. It has 4 different model sizes, but not too much. Let's go back to the paper. AlphaCode relies on a combination of powerful language models and a bespoke search and re-ranking system. So we're gonna be implementing something like, we need to implement ranking, we need to implement search, and we need to implement something like LLM inference, for sure. We're not gonna be fine-tuning at this quick video, but we're gonna be doing these kind of things for sure. When evaluated on the same platform as the original AlphaCode, we found AlphaCode 2 solved 1.7 more problems and performed better than 85% of competition participants. They provide problems from kind of lead code. So yeah, kind of problems that are short in description but hard to implement, mainly. So introduction competitive programming is one of the ultimate litmus tests of coding skills. Participants are given limited time to write code to solve complex problems that require critical thinking, logic, and understanding of algorithms, coding, and natural language. As such, it is a great benchmark for advanced reasoning and problem-solving abilities. AlphaCode was first AI system to reach a competitive level on this task. Its successor AlphaCode 2 leverages several Gemini-based models as part of massively improved system. So we're gonna be having LLM inference for multiple models. Alright. So when evaluated on the Codeforces platform, well, it's not LeetCode, it's Codeforces, we know now. A mainstay of competitive programming, AlphaCode 2 solved 43% of problems within 10 attempts. So we're gonna be trying multiple attempts. We're gonna just try 10. Close to twice as many problems as the original AlphaCode, 25%, while its predecessor performed at the level of the median competitor. We estimate AlphaCode 2 reaches 85th percentile of average. Alright, adopting Gemini as the foundation model for all components of AlphaCode 2 was key to achieving this level of performance. AlphaCode success underlines Gemini's flexibility and adaptability, as we were able to fine-tune it and optimize performance for several different tasks, including code generation and code re-ranking. So we're gonna be having different kind of tasks in here. We're gonna have code ranking, we're gonna have code search, and we're gonna have code generation. Right? Basically, the LLM inference is just gonna be the kind of the engine. So I think we're gonna be using the same engine to do these 3 kind of tasks, right? Okay. So overall system, AlphaCode 2 relies on powerful large language models combined with an advanced search and re-ranking system tailored for competitive programming. As detailed in Figure 1, its main components include a family of policy models which generate code samples for each problem, right? So the input for a model is going to be code problem. A sampling mechanism that encourages generating a wide diversity of code samples to search over a space of possible programs. Alright, that's interesting. So, multiple generations for the code. It doesn't, like, we have 2 kinds of different generations. We have multiple generations for the code, and then we have multiple attempts. I guess these 2 things are different. We're gonna be giving different models the same problem. We're gonna try to augment the things that they know about the problem, how to solve it by getting the output from all those different models, and then we're gonna be making that 10 times or multiple times. But this process will be repeated. a filtering mechanism to remove code samples that do not comply with the problem description. So we also need to do filter wrong code. Classing algorithm that groups semantically similar code samples. Scoring model, which we use to surface the best candidate out of each of the 10 biggest code clusters. Alright, code ranking, I guess. Yeah. I think these are kind of different models. Like they have scoring model, they have classing algorithm, right? With a difference between them. Filtering mechanism. What I was planning to do in here was just trying to use a general purpose LLM, like for example Llama, for pretty much all the tasks. Let's say if we prompt engineering, we can get something out of it. This is how it works, apparently. So, policy and fine-tuning. Our starting point is the Gemini Pro model, on which we apply 2 consecutive rounds of fine-tuning using goal as a training objective. First, we fine-tune on an updated version of code contest dataset containing more problems, more solutions, and higher quality, manually created tests on the validation set. So let's get something done. Even though I'm not planning to do this fine-tuning, let's take notes on how it is done actually. So Gemini Pro starting point. So this is basically our general model. And then we have 2 rounds of fine-tuning with goal. I don't know this goal algorithm, to be honest. So this is something to do. And then we have dataset. And it's gonna write the code, the code problems. I guess this is something like this. Like we give it the problem as an instruction, and we're just hoping for a solution to happen. Okay. We also have some reference on which are the amounts of different 50k problems. And we have 30 million human code samples. So 30 million code samples. We generate several fine-tuned models by varying hyperparameters and end up with a family fine-tuned model. So something we need to know is different models are fine-tuned with different parameters. Hyper. We could think about it like using LoRa on different parts, using different weight decays, using different learning rates, using different, I don't know, but yeah, different kind of these things basically. Relying on a family of policies instead of a single one allows us to maximize diversity, which remains key to tackling hard problems. Okay? That's interesting. So this is one of the main points that when I read it was like, wow, this is huge, because Google is trying to bring a lot of the techniques that we're just using on the state of the art of open source LLM systems. Like if you think about the approach from OpenAI, it's very likely the same thing, but they are just selling that they have a more performing model, not that they're just bringing all these things together in order to make the system better. Like I don't think it's just one LLM that you just prompt and just get a response. I think there's kind of a lot of things going on behind the scenes. Yeah, very likely. So sampling. Our sampling approach is close to that of AlphaCode. We generate up to 1,000,000 code samples per problem. That's quite a lot. I think we're gonna reduce those numbers quite a bit for this demo. So up to 1,000,000 code samples per problem. Using randomized temperature parameter for each sample to encourage diversity. So right here we're gonna have 1,000,000 code samples. Randomized temperature. I think we're gonna give it a range, right? Because you don't want to get a very high temperature because it's gonna go off the rails. It's gonna go something like gibberish, or maybe it's gonna start just outputting something that doesn't have anything to do with it. Like, we don't want code to look like if it were a poem or something like that. So it's like we're gonna give it a range. We also randomize target metadata included in the prompt, such as the problem difficulty rating and its categorical tags. This is huge. So we're gonna have something like prompt. It's gonna have the code problem. I wrote something in here, but I'm just gonna write kind of the prompt structure we're gonna give it. Code problem. And these two are randomized. That's something huge. Like, why do you use randomized tags? Yeah. Like, possibly if you're just giving it a sample, it may be easy, and you're just saying, no, this is difficult because it's randomized. How is it gonna improve the model performance? I don't know. So we split our sampling budget evenly across our family of fine-tuned models. While we sample in Python and C++ for AlphaCode, we only use C++ samples for AlphaCode 2, as we found them to be higher quality. So this is basically solving C++ problems. Let's supportive programming. Okay. Given the amount of samples, filtering and re-ranking are of paramount importance to the overall system's performance, as we only submit a maximum of 10 clone samples per problem. So yeah, finally, what we're gonna do is evaluation. Does any of these 10 solutions solve the problem? Yep. Okay, so filtering. Each competitive programming problem contains at least one public input-output test indicating how code samples should behave. So we're gonna be doing unit testing, one plus, so one plus, because it has at least one, right? So one plus. We execute each code sample on the corresponding test input and filter out all which do not produce the expected output and therefore could not have been coded, as well as the less than 5% of samples that do not compile. On average, this filtering removes approximately 95% of the samples. So filtering, filter wrong code. So what we're gonna do is basically wrong code does not compile, right? And second one is I don't know what did they mean by do not produce expected output. I think maybe this has to do with the format. Like if you ask code and well you see that it's a poem or something, like you don't even try to compile. I don't know. Like possibly if it compiles but it just have poems inside. I don't know. Well, we'll see. So clustering after filtering. So first we need to do filter, right? Second, clustering. After filtering, we are left with an average of 50,000 candidates per problem, but we limit ourselves to 10 submissions, right? So we're only gonna use 10. Like, I think we're gonna go either random 10 out of the whole thing, or possibly the first 10. To filtering down candidates, we aggregate samples based on their runtime behavior, right? So runtime behavior. Then AlphaCode, we train a separate model to generate new test inputs for each problem. We train a separate model to generate new test inputs for each problem. So we also have input generation, like program input generation as a task to give the LLM. As in AlphaCode, we train a separate model to generate new test inputs for each problem, then execute the remaining examples on those inputs. The produce outputs from a signature that we use to group similar code samples together into cluster. So the produce outputs are basically what we're gonna say for the different tags, right? So random behavior outputs of it is the tags. The cluster labels. Right, this is quite easy, I guess. It's not some huge complicated thing to produce. I basically produce the output of the program. You're gonna say that somehow, and then you're gonna use that for clustering. I guess we're gonna be transforming that into vectors in some way. So we're gonna likely vectorize that thing, or possibly we're just gonna use string metrics for distance between them. So for example, if we have two different strings and they're very similar, they're gonna have this very low distance. We're gonna just group them together. Then with respect to others that are quite different, I don't know, something like that, I guess. We order the clusters according to their cardinality, only keep the 10 largest. Okay, that's interesting. So the winning clusters 10 largest. I don't like that because it is possible that we're gonna have our 10 largest models outputting gibberish or outputting something that doesn't have to do with the things it should do. So I don't like it, to be honest. I would look for another metric, like for example, try to discard the clusters, right? So you first generate the clusters, then you try to filter them on gibberish clusters or not before the filtering happens or after the filtering happens, because the filtering is basically just telling you which of them are compiling, but then there's gonna be a huge amount of them that are gonna be doing gibberish things. Like I would also add in the middle something like you measure how likely the code is right with another LLM. Like you give it the code, you give it the problem, and you fine tune the last layers to be classifiers, like possibly binary classifiers. Yeah, I don't know, but I like this one, to be honest. So the point of clustering is to avoid redundancies. Since code samples in the same cluster behave similarly, we can submit a single one per cluster to the online judge to obtain the best result. The scoring model, we fine-tune a second Gemini Pro model to attribute an estimated correctness score between 0 and 1. So scoring. Okay. Using this scoring model, we compute a score for each code sample in our remaining clusters. We then select the best candidate sample out of each cluster based on this predicted score to form our finalist 10 submissions. So score all the outputs from the 10 biggest clusters, and then choose highest score sample from each cluster, submit the 10 winners. Right. Evaluation. We evaluated AlphaCode 2 on Code Forces, the same platform as the original AlphaCode. We selected 12 recent contests with more than 8,000 participants, either from Division 2 or harder Division 1+2. This makes for a total of 77 problems. Alright, so test set. For each problem, we sample 1 million candidates and submitted up to 10 solutions selected and ordered accordingly to the procedure detailed above until either one correct solution was found or we ran out of candidates. Wow, that sounds like brute forcing. We found AlphaCode 2 solved 43% of the competition problems, a close to 2x2 improvement over the prior record-setting AlphaCode system, which solved 25%. Mapping this on competition rankings, we estimated AlphaCode 2 sits on 85% of on average. It performs better than 85% of entrants, ranking just between the expert and candidate master categories on Code Forces. This is a significant advance over AlphaCode, which only outperformed an estimated 46% of competitors in the two contests where it performed best. AlphaCode 2 outperforms more than 99.5% of competition participants. So this is something huge. This is something huge. Pretty much everywhere. Yeah. Look at this. We evaluated the impact of, increasing the amount of samples per problem. As was the case for AlphaCode, we find that performance increases roughly linearly with more samples. AlphaCode 2 requires about 100 samples to reach the level of performance of AlphaCode. So AlphaCode 2 requires 100 samples with 1,000,000 samples. Wow, this is great. So if we don't wanna go for 99.5 or 85th percentile on the code candidate master and expert, or if we don't wanna go like 99.5 of participants, and we just wanna reach the AlphaCode performance, we don't need the million different elements from the testset. For the clustering, for generations. We just basically need 100, which is great. I think we're gonna be using these kind of numbers. Rather than just going 10 million, we're just gonna sample for 100 or even less. Alright, discussion and conclusion. Competitive programming is very different from other coding tasks which usually follow In product paradigm, the user specifies clear instructions and the model outputs the required code. Yeah, possibly for the for this implementation, we could just gonna go something simpler, like possibly not just coding problems like lead code or competitive programming, but something similar, something simpler. So in contrast, competitive programming problems are open-ended. To solve them before writing the code, the implementation one needs to understand, analyze, and reason about the problem, which involves advanced mathematics and computer science notions. This explains why generally available AI systems perform poorly on this benchmark. AlphaCode's 2 success on competitive programming contests represents an impressive step change in performance on this extremely hard reasoning task. This is huge. Yeah, possibly we're just thinking about LLMs coding on simple problems that we give them, like hey, write a code to call this request, or write a code to, I don't know, yeah, simpler ones. According to adapting Gemini Pro as our foundation model led to significant increases in performance on two critical components of the system: the policy models generating the code samples, yeah, and the scoring model used to select the best of them. Yeah, these are possibly the hugest things from this paper. Like, which policy are you gonna use to generate the code samples, and how you're gonna score them. I think the second is harder, like how you're gonna score them, because the first one at the end of the day is basically using the fine-tuned model. You can probably give instructions on the prompt, or you can just try to add some hidden tokens. I don't think Google keeps doing that. Like in the early days of T5, Plan T5, and all these models that Google developed, they were encoder decoder, and basically the output of the encoder served as a kind of a rich latent state that they could use to add custom instructions. But nowadays we just basically give the different instructions in the prompt, and basically what the ecosystem is moving towards is basically just using a decoder only. Yeah. So instead of just doing the first encoder, like why aren't we using encoder decoder? I think possibly it has to do with performance, because you need to do the encoder step. That's gonna take longer. Like it's like doing a by tries. The time it requires to do, possibly not by tries, but it's gonna take longer to do the inference, and it's also simpler. It means you have less parameters, and it's very likely that the decoder itself is capable of taking the task from the encoder without it needing anymore. Yeah. The fact that we were able to fine-tune Gemini to high performance for these two very different tasks speaks to its incredible flexibility. Wow. We suspect using Gemini Ultra as a foundation model instead, with its improved coding and reasoning capabilities, will lead to a far improvement in the overall AlphaCode approach. So it's very likely that Gemini Ultra is quite huge, because if they haven't used it for that and they just use Gemini Pro, it's very likely that it has a lot of parameters, a lot of cost, or very likely that they just were waiting for Gemini Ultra to finish and just release both papers together. Because this happened before NeurIPS or NeurIPS, or how you call it, this AI call for papers conference that happens. It's the huge for the AI ecosystem nowadays. Like if you're a researcher, PhD student, you're doing something on AI, your dream is very likely to publish on NeurIPS and just go there and show your paper on a poster and all that kind of stuff. That has to be huge, to be honest. It has to be really, really engaging for someone that has dedicated a lot of time to research these kind of things, and be able to be accepted on NeurIPS. Right. So despite AlphaCode 2 impressive results, a lot more remains to be done before we see systems that can reliably reach the performance of the basic encoders. Yep, our system requires a lot of trial and error and remains too costly to operate at scale. Well, that's basically what we just kind of the intuition that we got from this paragraph. Fire, it relies heavily on being able to filter out obviously bad code samples. Oh, this is bad. This opens the door for a positive interaction between the system and minimum coders who can specify additional filtering properties. In this AlphaCode 2 plus human setting, we score above the 90th percentile. Wow. We hope this kind of interactive coding will be the future of programming, where programmers make use of highly capable AI models as collaborative tools that can help them reason about the problem, propose code designs, and assist with implementation. We are working towards bringing AlphaCode 2's unique capabilities to our foundation Gemini models. This is kind of how OpenAI had their coding model that did only code. I think there's nothing like that nowadays. Like they just removed that one. I don't remember how it was called. I think it was called. Yeah, I don't remember. As a first step to make this new program paradigm available to everyone. Yeah, this is huge. These are contributions and some references. Yeah, sounds great. As I told you, this doesn't look like a paper itself. This is more like, yeah, this is what we kind of did. These are the results, and basically we're gonna try to tackle this problem from here. So just let me do something. Yeah, in this way you can just see it better now. AlphaCode 2 technical report. So this is Gemini Pro. This is the fine-tuning process, so we're not gonna be doing this today. We're not gonna be doing this fine-tuning of the scoring model, all that kind of stuff, Alpha 2 code models. This is basically the first step that we're going to do. And we're gonna be checking on different coding models, and we're gonna be doing this tiny. So the main reason for that is just to save time and save GPU VRAM mainly, because I have a 3090, but that's not too huge for scaling this. It's very likely we're gonna be doing something for testing. Make sure that we can do something similar to this. So in this problem, just basically code forces, alright? And then AlphaCode 2 models, they receive the code, all of them. Don't remember how many of them. I don't know if they tell how many models they have. Well, yeah, massive sampling, executing filtering, C++, C++ clustering, re-ranking, scoring model, and that's basically it. Yeah, we need to do a lot of things, and there is something huge in here. Like we're doing C++, so we're gonna need time to compile the code, which is something you don't need for Python code. Like for Python code, that's basically try to run it on the interpreter. Finger crossed it doesn't do anything like RMRF or something like that, and just basically destroy your computer. But yeah. Yeah, this is gonna be C++. We should run this on a virtual machine, something that cannot damage anything on my machine. But yeah, let's try to start coding. This is basically some nodes. I think I'm just gonna leave these nodes as rename, so it's gonna be rename, right? Yeah, this is not great. That is not great at all. So rename nodes txt. That's better. Yeah. All right, now let's go for main.py. So something we need to do first is let's try to look for different models. That we can use. So what about, let's try it out Phi2. I'm planning to do something like GitGoof, so I don't think Phi2 is implemented on GitGoof. Well, it appears to, but we're likely gonna need to do git pull, go to a 13 branch for that. I don't know. Let me check. Oh, something did it. Well, this seems like, yeah, possibly we can try later, because this seems like it's not 100% tested, or it's in a branch. So yeah, let's do something simpler. Replit is also quite hard to have it running, because the architecture is different from Llama. So let's try. It was 6 months ago. Yeah, with a code was quite good, to be honest. But we need something quick. We need something like 7v, for example. And we need also C++. That was small open air miss. This one is huge. Yeah, this one is huge. 2.5 Mistral 7v. Yeah, I don't know if there are some kind of coding benchmarks, just coding benchmarks. But this one is quite huge. There's a lot of people using this one at the moment. So I'm looking for this, but in Google. Yeah, we don't need a huge contest window, I guess. Yeah. Yeah, this one. And I'm gonna go for something quick, like Q3K. This usually works fine. Yeah. This one. 3.52. I'm gonna save it. I don't have access right here. Yeah, let's wait to download this. We're gonna also try to download other models. This one is gonna be huge. Let's try that. Yeah. Let's try something with Q2 because there's a lot of going with Q2 these days. Let's see if it gives any interesting answer. Yeah, these models are quite like we're not using like bfloat 16 or all the like all the bits. We're just using the quantized models because they're smaller, they're gonna load faster, they're gonna do inference faster. We don't want Python, we want C++. So code challenge, I guess. So we need the data set, we need the problems to give them the models. Code contests from DeepMind. That sounds great. When did you release this thing? Or 6 months ago? Or a year? Over a year? These are Parquet files. Wow. Wow. The problems are quite difficult. Like, this is a quite long description of the problem, honestly. Yeah, it's very likely they used code contests. What was it called? Code contests? How did they call it? Yeah, code contest dataset. That's the one used. We fine tune an updated version of code contest datasets. Yeah. On an updated version, possibly not, no, likely not the one that we have access to. Yeah, that's possibly quite too much for testing purposes. We're looking for the code, not just for, you know, we're looking for the code. Let's download this one and let's use. Yeah, let's download this. Just the first part of it. Let's try to see what we can come up with. But these are quite hard coding tasks, code instructions. Well, it gives a programming language in here. We're looking for C++ only. Yeah, this also gives create Java application. Like, this is possibly gonna be the hardest part to find. Oh, StarCoder was also a good, yeah, programming model. StarCoder. I don't know what it was trained on, to be honest. Yeah, a lot of programming languages, so this one should be good. Start coder. I don't think we have access to Guguf, Giguf, however you call it. Yeah, someone has. Alright, let's get this one as well. Let's download StarCoder as well. So we have how many of them? 1, 2, 3 models. And likely we're gonna be using this data set. I think that's too hard for a model. Like, it's gonna be difficult for it. Yeah. Yeah, I don't know. And you see, guys, this is the hardest problem, to have a data set. Code, like, if we have code Python, this is gonna be hard because pretty much everything is trained on Python. Then we have, yeah, of course, C++ and many others, but pretty much everything is on Python. And the main problem in here is, like, you call in Python lists what you call in C++ vectors, arrays, whatever. So the terminal is gonna be different. So I'm thinking about just doing Python. Yeah. Just doing AlphaCode for Python. AlphaCode 2 for Python. Yeah, this is gonna be great. And this is gonna be different. And we're gonna save the process of compiling the different generations. And we can try to detect whenever the Python code starts, because we have much more code Python. Yeah, as you can see, there's plenty of them. Python code instructions 18k alpaca. Yeah, this is kind of easy. This is kind of easy for the model to do it. Like, it's gonna be easy for it. Yeah, I like this one as well, to be honest. It's quite small. Yeah, not too big. Data. It's gonna be per k. Yeah, per k. So let's have a look at this Python code instructions 18k alpaca. Something we can just get our hands on faster. Alright, and we have open enemies, wizard coder, and we have these two parquets. Train, it is a train one, I guess. Yeah, this one. I'm gonna start creating here this data set or data, and we're gonna move in here the models as well. Okay, that's great. Let's get our hands on these. So let me check the names for the models. Let me get first to city, desktop, paper reads, unless we need to do word to bed at some point. That was my first plan, but then I thought, hey, AlphaCode 2 has just released, so what about just making this? Alright, city code. We have city models. Alright, so MV. Almost done. Yeah, almost. And as you can see, I'm just downloading the GitHub. What I want to do is basically load the models on Llama CPP. Like launch a server with Llama CPP of the different models. I hope we can just have them all together on the GPU. hopefully it's gonna fit, and then just route the request to the different models and get the responses back and just take notes of that and all that kind of stuff. Yeah, that's my plan. Instead of this going Hugging Face, load, all of that, whatever. Yeah, I think that's gonna be faster. We are likely gonna have problems with the contest window, I guess, possibly. I don't know how the server works on I'm gonna say it, Llama CPP. So move, how they're called, stack order. All right. Oh, this is GGML. I don't think this is gonna work because we have gigoof. Whatever. I have all the models we can try. So MB home PC downloads train with a coder. Yeah, with her. Here MB home PC downloads open HEMIS. We have two models now. Yeah, possibly we could use Wizard Code 13b if we're just gonna do Python, but whatever. And then I have all the models somewhere, so just let me check. MB home PC desktop CP I think it's called all right. The models. Let's try no means Llama 2 13b as well. So no means Llama 2 13b is quite older than this one. This is also 7b, this is 13b, and this is 15b. So these are the models, I guess. These three models. It's gonna be fine. And now what we need to do is basically launch the process. So port OS. I don't know if we're gonna be using OS. I don't think so. Requests. And now dev. We're gonna make a function to llama cpp generate. We're gonna give it the URL and the prompt, right? So here we're gonna have headers, and this is gonna contain content type. We're gonna send it an application JSON. We can also give it mpredict, but I think it's on the data. So data is gonna equal prompt, I guess it was. Then we can give mpredict, but I'm just gonna leave it this way. I want just to generate the whole code. Like if he has to do more code than just a certain amount of tokens, I just want that. And then we're gonna go request.post URL equals URL, data equals data, headers equals headers, response equals this, and then we're gonna print response dot text, I guess, or to this. I don't know if it's gonna be, that's gonna be working. And then return res. So we need to open up the data. We need to define the data as well. We're gonna be doing, what did we say? How was it called? Train 000 of 0001. Alright, so just let me copy this thing here. Copy link address. Alright, so now what? Alright. Yeah, right. I don't think we're organizing this correctly. Like we should have data right here, paper in here, and code in here. Yeah, the problem is gonna be when we try to access data, we just need to move out. Now let's move it here. We have data, we have models, we have the code, and the nodes. That's great. Right. So now let's open up this data. I'm just gonna go for pandas, I guess. If I remember right, we have pd.read parquet. Awesome. Data. Rename. Copy. Oops. Paste. Parquet. Let's see. Yeah, well, works. So we have prompt instruction. Let me get the columns. Yeah, it's not a function, it's basically an attribute. Sorry for that. Instruction input output prompt. So this is basically because it is alpaca. Yep. So this is basically 18k. Let's do sample equals 10. And then let's do this instructions. Like let's get the first 10 rows. How was it in pandas? iLog. So sample site. Let's get now this as a list. Let's get the input, the output, and the prompt. So prompt equals the same basically, but we're just gonna get prompt in here, then input. How's it called, like because there's something in Python called input. I cannot call it this way. So input data. Yeah. Yeah, input. Then code out this thing. Right? And then we need to get, well, basically everything is basically right now. Input, output, prompt, instruction, good. Now let's print instructions 0 from 0, print code in 0, oops, print code out 0. Yeah, all of them. And let's see which is basically the first element. Yeah, something wrong. Oh, didn't save. Alright, so instruction basically input bang, output bang. So our objective in here is like, why do we have the same code twice? Wow, it's repeated. Let me separate, let me check what is inside everything. I'm quite confused now. So we have, this is the instruction. This is the prompt. This is the input, and this is the output. So, yeah. Like we want the code to generate this thing. The code input is gonna be used for the testing purposes, basically. But we don't have the code output. We don't have the sum of the sequence. We cannot test that thing. We should take the code out, run it with coding for evaluation. Yeah, in order to evaluate this thing. Yeah, let's do it. So if evaluate, we're gonna receive code in code. Let's call it func parameters and code. Yeah, possibly I should just call it the other way around, more natural. Right? We're gonna receive code parameters and function and code. We need to evaluate the thing. We need to we need to just trust the data set that it does have nothing like could damage our computer. Yeah, code function parameters. Yeah, Yeah, that's incomplete. Like, why didn't they add this to the training data? They should have, right? Because now we have to run the whole thing to evaluate the code. All right. So I think it's gonna be exec code, but it's not gonna be code. We need to do something about it because we only gonna have we only gonna have we're only gonna have the function. So we need to call the function on the sequence. So we need to do some underscore sequence. So we need to identify the beginning of the call, like this thing. Yeah. So we need to look for def, then get the name of the function. Yeah. Def get Python py functions. We get that, like, if we execute a code, we also need to execute a code. Yeah, and we could get the name of the function, but let's do something quick, like something like code, and we're just gonna basically I'm gonna go for code lines, blocks, lines of codes. We're gonna get code that split like this, and then we're gonna go for line in log. For each line in log, we're gonna if def inline split line split we're gonna go for def space -1, so we're going to get the rest of the line, and then we're gonna do split on opening parentheses, and we're gonna get 0, I guess. Yeah, something like this. We're gonna break in here. Oops. And we're gonna return res. So res equals this. And if we return empty, we know something will happen. The py functions. Well, singular. Alright. So if there are more than one py function, we're gonna just receive the first one. I don't know if there's many functions on the code or not. Let's keep this code for now. Oops. Yeah, get py function. So get py function, we're gonna give it code. I think it was code out. Yeah, code out. We need to rename this thing, like generate code or code solution. Code result data in or code params. Yeah, code params. And then prompt is fine, instructions is fine. Yeah. Now we need to change this thing in here, like code res right here and code parameters in here. Better now. Code res this here. Res by func. Yeah. Oh god. Alright, let's go. Yeah, wrong. So code split. Oh, because this is a list. Yeah, of course. Yeah, let's hide this in here. Alright. Yep, some sequence. That seems fine. So, code to run, it's gonna be equal code plus, let me get py function, let's give it code, py name, func name, or fun name. Yep, it's gonna be fun name. Well, let me do this like this, plus fun name, and now we're gonna give it fun parameters. Oops. We need to also add. Sorry, I meant this. Yeah. Oops. And now fun parameters class, and let me just add a C here just to make sure the name is the same. Yeah, like the same format. So this is gonna be the code to run. Print code to run. Yeah. Better. Let's go. Evaluate, we need to give it code, so this is gonna be like code res func parameters, so it's gonna be code params. Yep. Can only concatenate list, not string to list. What's the matter? I think it's the same matter as before. So basically code equals code here. So what's going on in here is we are just taking the list from pandas, but basically it's going to contain yes one element as far as I know. Oh no, we need to do something. No, this is wrong. This is wrong. We should be doing this in here. Sorry for that. Yeah, my mistake. Yeah. Code split. Let me print that thing in here. Let me check what it is. I think I know what's going on. So, oh, sorry, line 13, this one. So yeah, we received the whole thing. Oh, because we're just getting this calling here. Get py function. Yeah. Bye-bye. Great. Okay, so this is what's going on. So evaluate, print code, don't print it. Just the code to run. Yeah, so we will have this in here. This seems like fine. Yeah, now we can just exit the code to run. So code out equals code to run. Oops, sorry. And we can just print code out. Yeah, so the result is none. Yeah, we need to do something more. So code res equal Mm. No. Something that we can make sure that there's nothing wrong. What's going on? Function return equals code. Oh, because we have Python coding here. Oh no 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 no. Sorry for this. This has to happen right here. Yeah, function return is not defined, but this is basically what's happening in here. So I have done it before, but don't remember how. From Python exec into IO. Yeah, I've done it before for one of the repos that we have at Dart, but I don't remember how. Python exec get output. Oh, we need to redirect the output. Wow, this is huge. I didn't remember this to be that hard. Yeah, let's try this one. Let's see what happens. Not here. That's basically, sorry, on the evaluate one. So f string with redirect output help. What's the help thing? Help how? But how is help? This one. Oh, we need to import sys. So we're not using always. Let's go for sys. Basically, what's going on in here? All is the out. Now we just basically get the code, I guess. I'm not sure. Yeah, it's a code, so it's not called code, but it's called basically this one here. And I don't think we need to do this. Yep, I don't think so. And where's the output? Function return. This would be the output, right? But these guys are just printing the output in here. They're just printing the output in here. Yeah, that's not gonna work for us because we don't have print statements on the code. Yeah. Right, we don't want this thing. Yeah, my result. So this would work. In a minimum example. Yeah, that's work. Yeah, that's exactly how I remember this to be honest. But I didn't know why. I print code to code. Yeah, let's see what happens. Function return. Oh, this is weird. Oh, exec, but it doesn't use. Oh, I'm not doing the exec anywhere. Go to run. Yeah. Vale. And function return is not defined. Hmm. Get value of Python of variable exec. Hmm. Use eval instead of eval instead of exec. So if I do eval, how is this invalid syntax? Oh, because we have multiple lines, we cannot use eval. Yeah, that's it. Yeah, we could do something like this possibly. Exec can return expression and then you just basically get the value back. Yeah, this could be helpful. Return eval. Yeah, that could be helpful, I guess. Let's see. So we basically need to give exec can return. Oops. Not in here. Not in here again. Oops. Copy, paste, print. Alright, and basically we're just gonna get this, right, and we just need to give it a name. This is gonna be the name. Alright, does it work? Valid syntax. What if I do the following? No, doesn't like it. We're looking for something like x eval. So function inside x string exec and return value. Oh, so we need to, all right. Will this work? Oh, we're looking for function return, I guess. Yeah. Wow, works. Right. Right. Yep. Do we need this line, I guess? Nope. That can disappear. With this command, alright, and then just do def exec and return. We just need to give it code to run. So instead of print, we're gonna do return this. I'm just gonna leave the print comment because that's gonna be helpful at some point, I guess. Mainly if we want to redirect the output from the model inside the prompt of the next iteration, that's gonna be helpful to have the result right next to the output, I guess. Alright, and this needs to go in here. Right, and we need to give code to run as a parameter. Yep. Awesome. Basically this is gonna work. Yeah. Oh, we need to do exec and return. We need to give code to run. Yeah, and this is gonna be result train res. Yeah. Alright, and now we're just gonna go for so evaluate code func parameters, and we can reuse this function for generative code. Like we can use it for the test bench and for the generative code as well. Yep. Do we have output? No, we don't have output. We need to improve the dataset before just getting started, I guess. Okay. So let's do if we give code and fun parameters, it's gonna run the code. But what if give it an unexpected output and we just check if it is true or false? Sorry. Free result, yeah. So we need to give it like true or false, because if it is right or not. So this is not evaluated, this is more like run code with parameters. Get code output, I guess. Yeah. And now we can do def get evaluation. Which basically we do is return res. Get code output, we give it like code, func parameters, and we also need to have the output say code, func parameters, and then the output. Right? So basically we're gonna run this thing. We're gonna have the obtain output, right? And we're gonna check return obtain output equals output. And as everything happens in a string, like your language model only knows about strings, and everything happens on the string ecosystem, because we don't have typing as far as I can tell in language models. Like if you see a 3 on a prompt, that prompt is string. Like that prompt is doesn't know about 3 as a string. Like you would need to go for double quotes, and I don't know if inside the LLM itself would know that it is a 3 as a string or a 3 as a number. I think it would end up knowing because you train it for that. If you give samples of it on the train data set, but otherwise I don't know. Like that's something to do. Like give typing to things that happen on the LLM prompt. Right, get evaluation. We're gonna go for get evaluation code res code params. We know it's a 15 the result. Basically return so ev print ev, and in this manner we can see if there's any mistake. Oh, there's mistakes there. Let me tell you what we have. How do we receive a number? Yeah, it's like we receive a number from the code output. Yeah, so even though the LLM doesn't know itself, it's an integer string, we know because of the Python typing, because we have run the code, right? And we have given 1, 2, 3, 4, 5, and these are integers in Python. So Python understands the typing, the LLM doesn't. So as we are evaluating with Python, we need to make sure that typing is respected. Great. So get evaluation, that's all. Now we can just basically give all the different codes this thing, right? And we have only tried for 0. And we need to first get all the outputs, so get code outputs, and we need to improve the data set. Whatever it takes. How do we improve the data set? Like we have data in here, sample in here, code results, code parameters, code output, I guess. It is not code res. This is code label. We're gonna have trouble later, but this is code label by now. Code label, like the truth, like all code truth. And code output, yeah, it's gonna be a list for LM in instructions. We actually don't need instructions yet, we're just doing code. So basically code truth y, now we're gonna go enumerate this thing here, and now we're gonna go for get code output. We're gonna give code, So this is gonna be like code truth I. Well, we can just say LM, code LM. This is gonna be code params I. Oh, this is code param I. Then we have code LM. Yep. And then we're gonna go for return val equals, and this is get code output. Yep. And now we're gonna just go for return val. So I'm gonna go code output append return val, and we're gonna print them. Yep. Oh wow. Yeah. What is this? Like grow website for phone numbers. This is weird. Oh, because there's no way. No, this is a function. I don't know what is waiting here. So how we organize this thing? Yeah, this one has print on a main, but oh, this is gonna be huge, man. Yeah, so function return equals scroll website for phone numbers. That's the name of the function. Then parentheses, then func parameters, and then close. But where is it? This thing coming from? Yeah, we cannot. Well, this is gonna be huge. We cannot stay in here just testing for everything. So I think we're gonna go for something like try except failed code. 1, 2, 3. We're getting a lot of output. Like, let's check out the rest of the code. Let's see. This was easy. This is gonna be huge. Function return. Oh, this doesn't even have a function. Yeah. But this work. This one work. How? Like, how do we evaluate these things? See, if there's no dev, we just wrap this thing on a dev. That's kind of easy, I think. And then we call a function. Remove duplicate string remove duplicate string result. Function return. Remove duplicate. Why this dig when this given a string? Oh, because we have. Oh no way. Wow, we have a lot of things to clean up, I guess. Yeah. we can fix this one quick. If there's no def, we just put everything inside def. How are you meant to test these things if you cannot just run the code like in an easy manner? It's quite difficult, right? How much time are we on this? Almost 2 hours. So we need to do something more like def wrap code funcs def, I guess. Something like this. And we're gonna give it code. Yep. So if what's it called? So we're just gonna be calling this function if we have no def for sure. So we need to check for that on a different part of the code. So basically result equals def function, how we call it, func wrapper. And we know for sure it's very unlikely it's gonna be something func wrapper, right? The func wrapper, yeah, that's the beginning. Now for line in code res plus equal, let's add a tab and plus line. We could use format print formatting in here, but let's do something quicker. Yeah, we need to tab everything at least once from respect everything that has been, you know, before. So basically then return res. Yeah. And then we should try to check if that fixes this one. So wrap code def get code output, I guess. Yeah, func name is, well, first of all, if no find function, if no function, maybe no function, wrap code def code. We also need to make sure we respect the parameters. Yeah, well, there's no parameters, right? Because we're just basically wrapping everything. There's gonna be no parameters, so we can just forget about that. So no function, no function, no function. Code or has code function. Has code function code. That's a much better one. And we just basically come in here def has code function code for line if return def. I don't know if code is a list at this stage. Is it a list? No, it isn't, because we're just playing with strings in here. Return def not in code. Like possibly there could be something like just writing. I don't think there's gonna be def. Nah, that's kind of weird. I hope. Yeah, has code function. If has return false, basically. Def not in. So if it is not in, no, this would be in. Return def in code. It has code function. And then if not has code function, then code equals wrap code def. So wrap code def is gonna just return this thing, bing bing bing, and that's gonna work, I hope. Let's check it out. Oh, things weird. Things weird. Alright, let's see. func wrapper. Huh. Yeah, it wasn't aligned, so yeah, it doesn't make sense. It was just taking them by characters. So code dot split new line. I think it works now. Yeah, the func wrapper. Oh, that's looking good. Func wrapper. Oh, we need to return. Yeah. So the last line is gonna be like return. Alright. Let's do something. Lock equals this for line in lock. And basically if let me do something like I enumerate. What I'm gonna do is basically just go through the log in, and if we are on the last line, it's likely that that's the thing we need to return. Very likely. Like if they have print, this is gonna be huge. This is one of the problems from LLMs. We have two problems. One of them is the data is sucks. Available data sucks. We need to tackle that in some way. Have some plans, but no time for that. And then the other thing is we need to work on defining how the functions or how everything is evaluated. Maybe it's easier just to give the problem, the parameters and everything to an LLM and say, hey, how do you see this? And it's gonna go like, yeah, this is right, this is wrong. But we depend on what the LLM knows. Like it's very likely it's gonna hallucinate a lot. So let's try to do this. Yeah, possibly we can write another function that says, hey, this is your prompt, just evaluate this code. Is this code right or not? Or just give an evaluation, 1 to 10, whatever. So for I line enumerate code, if how's it? I equals size len lock. And we're not gonna get on len, so it's gonna be len -1, I guess. What we need to do is basically else we just need to do return this. Oh, just basically with a return, sorry. Plus line, yeah. And this is working now. Wow, we fixed a code. So this failed code is coming from the previous, this one now working. Let's print something in between so that we can just have a look better. Like print yeah, much better I guess. So we have some of them to fix. Like some of them are quite hard. Like we need for example, well, we have the dependencies, but we would need to have a database, I guess, right? So that's gonna be harder. Yeah, this kind of code is hard to test. It's palindromes. We have return in here. Function return is palindrome. But we have all this in here. No way, man. Why does it happen? Oh, we have more than one output, I guess. I have 22, 3, all these things, 15, and this is working as we expect, and then we have this and this. And this is a failed code, and don't know why. Oh, because of this. Oh, because we split the code on... Yeah, we need to add something. So we need to add plus n and plus slash n, because what we did in here is basically we just split the code, so we just remove all the slash n at the end. That's this weird code in there. As you see, this one is working now. Let it suit. We have these blank lines, but I don't care too much about them. Yeah. And this one is failing because of, whoa, because this code is wrong, I guess. What about indentation? I don't think we are just running this. This is wrong in the data set. Yeah, this is gonna be huge. This is gonna be a hard one, honestly. So, we have advanced up to this point. Yeah, and we haven't used any LLMs yet, just basically just running with the data and just understanding what the code is gonna be doing next. We have been around 2 hours in here, just reading and just trying to figure this out. So yeah, it's gonna be quite long. Yeah. But we need the man to evaluate everything. Code output, append, return val. And if not, we're just gonna append just something like error. During eval, something like that. All right. So let's get this done. Yeah. So what I'm gonna do is basically, if we yeah, it doesn't make sense if this is like, where is this 22 and this 9 coming from? Oh, this 22 is coming from here, good. And this 9 is coming from here, good. Good, so if it fails, it's not appending any value here. So we have 1, 2, 3, 4 out of 10. We have 40%, so the 60% of our functions are likely gonna fail because, you know, things happen. This is great. Everything's great. So this is the kind of thing we're just feeding the LLMs, just wrong code. So what do you expect? It's gonna just generate wrong code. Yeah, so 1, 2, 3, and 4. This is basically what basically is working for us. So sample size, let's go for 100, and then let's print working samples, then code output. Yeah, let's go. Oh, we have multi-choice as well. Wow, this is great, but it is not great for testing at all. The play game. What can we do about it? Like, if he has input, just skip, right? Well, there's a lot of them. There's a lot of them that require input from the user. So def code or has user interact, has user input. Yeah, that's better. So basically, what we now do is return input encode. Yep, good. If that happens, so has user input. Code output append has user input, and then continue basically. Yep, let's go for this one. I don't think he has truly understood. If has user input, this is basically returning input in code. Like, what is code truth? I think it's a string, right? Oh, it's a list. Oh, okay. Yeah, my mistake. Code LLM, now fixed. Oh, we have data visualization too. That's great. But we don't want to visualize things, to be honest. So we're gonna do something more. Def skip plots. Alright, so what we're gonna do is basically just comment those lines possibly, or just skip those lines. Yeah, I think skipping those lines is gonna be better. Basically just get some code in, and we're gonna do as well dev has plots. Yep, and yep. So if we find any plots, we're just gonna stop there. Like, absolutely. Let me check how that went. Like, bang. Alright, so PLT plot basically. So we just need to just stop this thing. Like, this is doing nothing. Like, it's gonna generate some plot. How do you expect this to be something to test for? Like, yeah, your LLM is gonna know how to do plotting, but how do you test that? It's kind of difficult, right? So yeah, we're just gonna stop this here. It's gonna return none, and that's gonna be it for today on this one. So yeah, plt.show if. I don't think, like, you cannot just then take plt.show as an output and put it somewhere else. I hope, because otherwise it's gonna generate errors somewhere. Like, if return in quotes, I'm just gonna go for .show, because it's very likely that maybe you're using sub-axis, I think it's called, when you just divide your whole figure into different sections and you just use the different AX all the show. So I think it's gonna be better. And now this is basically gonna be REST code. Yeah. So code log equals code. So basically res equals blank, and now code.split /n, like this one. And now for I line enumerate log. For each of the lines in the log, what we're gonna do is if has plots line, yeah, if has plots line, continue, else res plus equal line itself plus slash end. Yeah, just to respect everything we have removed on split. And then basically just return res. That will be it. I think, well, we don't have to enumerate things. Yeah, this is much easier. Great. Great. So skip lots. How do we do that? Like get code output, right? Get py function, code to run. Then basically we're just gonna run it on all of them. We shouldn't. If has plot code, so basically we're gonna skip lots code. Just like that. Yep. And I hope this is gonna fix it. Like code equals this one. Yeah, we need a lot of data creation. Yeah, it worked. Right. And now we just need to remove like error during eval or has user input. So has, how is it called? Has user input has user input equals this, and the other thing is basically error during eval, error during equals this. Alright, so basically, well, no, let's make it easier. I skip training or skip eval. I don't know how to call it. Skip samples. Right, so this one and this one. Great. Now we just need to remove like all the things from. Yeah, this is gonna be hard because we need to make sure that, yeah, we only keep the ones that work. So instead of filtering the whole code output, what we can do is just basically continue, and here is fail and nothing happens, and only if we get into this place we just basically append the value. Possibly this is much faster. Yeah, and then just basically code output append, and then we're gonna append everything else as well, like cleaned some, like clean code params, cleaned code truth, and cleaned, well, yeah, I'm just gonna call it that way. This one, this one, this one, this one. Yeah, this is gonna be for it. I'm just gonna close this here. Yeah, we're not using the paper, so we don't need it. Somehow I think we're just able to see the whole code. Alright, so code parameters, code truth. We're gonna go for, yeah, nothing after code truth, I guess. So we're just gonna order everything so that everything is organized as suit. So this is code truth, code output, like at the end, code parameters, like this one in here. Let's go for clean code parameters. Yep, equals list, like clean prompt equals list, and clean instructions equals this. Yep, good. This is so cumbersome. Like, this is not hard at all. Like, this just takes a lot of time, and it's like being a data entry, just for code entry, just for grid. It's kind of unit testing all the time. But this is what it is. Like, this is the future of programming. Absolutely. Like, I think this is basically what we're gonna be doing in the next years. Just training things for the LLMs to learn and test and make sure everything goes straightforward. And we're just gonna let the LLMs do the fun thing. Absolutely. Alright, so this, and this. Code params, this is repeated. Code truth, code params, code output. I think we have everything. Yep. And now we just need to just put everything in here. Like, I'm just gonna be organized. Gonna append, and then it's gonna be instructions, and it's gonna be I. Right? Clean prompt, append, prompt, I. Cleaned code params, and code params I, and return eval. So we have instructions, we have prompt, we have parameters, we have output. Return val. Oh no, sorry. Like, I'm sorry. Good truth. No, code output. Like, what have I done? Oh yeah, return val. Like, this comes from here, inputs in here, and then the rest is code params. Code. We have one more pending. Code truth. Like, clean code truth dot append code truth sub I. Yeah. So clean code output is basically what we come from here. We just call it that way. Clean code truth, code params, code prompt, and instructions. All of them, like these 5. Yep, we're fine to go. Now let's have a look at clean code truth, and let's see the code truth. That's what we have. Yeah, I don't know if this will be trained or not. Let's go. Yeah, we had a lot of samples, so let's go for 10,000. Oh wow, we're getting fun things in here. This is so dangerous, man. What I just did. This is so dangerous. Oh wow. I'm just gonna close this window. Yeah. That was so dangerous doing. Running code you don't have control over. That could be doing anything, like killing processes or whatever. Yeah, that was so dangerous. There's a lot of stuff going on. We have Pygame. Yeah, this is gonna be fun. So we have, let's go for 1,000 samples. Right, so let's go to code. Oh, it has even created files and databases. This is so dangerous, man. We should have run those programs on a virtual machine or something. Yeah, I'm just gonna remove these things like my database, sine wave, user data, DB, user data, JSON. Let's leave this here. But there's no other way. Like, someone needs to do this, right? Alright, so this will stop with this Pygame thing. We're just gonna skip Pygame. Like everything, like we cannot measure anything from Pygame. Like even the plots, okay, just plot them, just skip them. Yeah, but you can also do anything with those plots. So the same is gonna happen with Pygame. Like how can we measure that? So we're just gonna skip this thing. Return Pygame encode. Okay. So if or has Pygame code LM, we just skip this thing. Right. So now we have 159. That's quite a lot of working. Is that for real? Look at those numbers. No. Oh god. Alright, let's go. Now we still have Pygame, but we're gonna have some, yeah, domain example.com. So which is the code from, let me check. Like this is dangerous because someone just knowing that if he could come in here and just say example.com and oh wow, it exists from Ayana. Wow, you know that. So def has URL run example.com encode. We don't know which one is it, right? Yeah, we don't know that. So or has URL code LM. Great. Okay. We have 157. That sounds great. Now, what if we go for 2K of them? Are we gonna have so many surprises? Oh, this is this is taking too much time. Just trying to calculate the square root. Can we have a timeout on the code? We're gonna also skip ticking there and while truths. So we're gonna skip those as well. Def has while true. Return code. We're gonna skip them as well. We're gonna give code. And that has ticking there. Oh. Yeah, it's way better. So basically we just run it again and hope for nothing. Well, we need to add these things in here. It's getting more and more complex. But as you can see, we can just kind of create profiles for code. We can just define these kind of tags. Possibly this is what they meant with tags on the code. I just start defining these things. Sorry. How can I just quit this thing? Okay. And this is just basically Python. Just imagine this doing this for C++. That's got to be hard. We need to give more recognition to Google. Because this kind of thing is hard, it takes time, and we just all the time, oh, this was a stage, this was that. But I think it's a lot of work to do these kind of things. Oh, did I miss something? Oh god. Sorry for that. Alright. And this is doing something. Oh, this is a server forever. Alright, def oops. So yeah, this is a lot of interaction. Like possibly we can train an LLM and tell them, hey, this kind of we don't want these things. If you find them on the code, just script them, and that is a great exercise to do. That would be great to see, but otherwise this is all done by hand. Alright, so we have 302 working examples in here. That's a lot of code. Let's go for 3K samples. And if there's no subplace, what do, like this is doing. So let's do something more. Let's check if he has nested loop. nested fors. We can give it like which is the complexity that we want, like n. Yeah, like if, for example, if he has an exponent, would be something like that. If he has, for example, 3 loops, nested loops, that means it's O and Q, I guess. So basically, we're gonna get like so log equals code dot split slash n for line in log if for in log. Let's get highest complexity or max complexity, max comp equals 0. So if for in log, we're gonna check how many nested loops we have. So basically, nested loop do get more spaces from the for before. Yeah. So we're gonna count. We're gonna do split on 4. So spaces like indent space or spaces equals log the split on 4. We get the prior part, and then basically we count them. Basically, spaces is the length of it. If we have tabs instead of spaces, this would work as well. Oops. Because the first would be the first part of the line. There should be nothing before 4 as far as I can tell. So spaces equal len on log split 4 0 basically. That's gonna be kind of a string, I guess. Yeah. Basically now max spaces equals, well, max comp equals 0. Prior spaces equals 0. So basically, a prior if spaces higher than prior spaces, prior spaces 0, spaces higher than prior spaces, prior spaces equals spaces. If spaces higher than max comp equals spaces. I guess this works. And if spaces less than prior spaces, I will always how do we do this? We need to know how many of them are, nested. So max comp is basically is plus equals 1, I guess. So we have spaces. If spaces is higher than prior spaces, we just update that thing. If it's lower, we update that thing. So we'll have something like this. For E in L for right, so basically max comp, let's mind we have 0, so if more, we just update that, and imagine we have in here this thing again. So if spaces is less, we update that, but we don't increase the max comp. So we always need to update the spaces that we have because they are nested. Yeah, this doesn't make sense. Yeah, spaces equals how many spaces equals how many spaces do we have, and that will be it. Yeah, we don't care. Like the more nested you keep adding, if space is higher than max comp, we just increase by 1. Yeah, just return max comp higher and next. Yeah, let's say we don't want like higher than 2, because we have much more than 2, right? Oh, we don't have the terminal anymore. So all the files again, right? So yeah, let's keep it there. All right. I don't know what it does, to be honest. So we have 1, 2. Oh, we only have 2. Alright, so we need to be higher than 2. Yeah. We only want 1 loop. Why are we running this thing again? Like, we saw them. Yeah. This is wrong. This is wrong. And this is wrong. This we don't need it. Yeah. Let's remove the SMTP as well. The SMTP. Well, let's see what happens. Oh, 397. Great. Yeah, for all these codes like SMTP, HTTP, whatever, we should create a unit test that would run a request or would just check if the request is sent or whatever. That's great. Yeah, it takes longer. So we're just gonna move through. We're gonna try to get the code running on the LLM. How much time are we on this? 2.5. So let's go quickly. You can see how many things are there. Right, so how was the code? SNTP, I guess, right? So he has return SNTP in code, just like that. Oh, haven't had it. Yeah, good. I don't know what happened. I don't know. Yeah, maybe that didn't bring anything or that just broke. Yeah, 397 working samples. It's kind of a tenth. Let's go for 5k. Is the tagging here? I was trying to do it. And I started studying here. I served forever. Oh god. Yeah. I'm gonna fix that thing. What was the other one that was stuck somewhere in there? Like. Oh, yeah. Well, yeah, I don't know if it was stuck because of the import error. Stock price. Well, it's gonna take a bit longer. Yeah. Def has ML, machine learning, and then this, and then basically code. Return has scalar. Now it should go faster than before. Oh, yeah, miss it. And just think about it, if we are doing if we're doing just also machine learning in there, there should be a way to evaluate the model that you train, you know, as the LLM to see if they come up with the same. Yeah, it's kind of complicated, and I guess at the end of the day, what we're gonna do is iteratively train the LLM on code. Just try to get some feedback to know which code runs correctly, which code doesn't, and at the end of the day, just try to make sure that the LLM knows the basics, and when the LLM knows the basics, you can just try to make the LLM, you know, an evaluator of the code, because otherwise this is gonna be just so cumbersome. Like there's gonna be the next 10 years is gonna be interesting because we're gonna be like this by hand if we want to make the LLMs, you know, train properly. 7,500. Let's see which kind of surprises we have. You see these kind of things, man. We don't want. Oh wow. So turtle has turtle. Also, nothing. Code. Return title if has, what was the other thing? Big number. If there's big number, you know. Alright, so how can we check if there's big number? How to check if there, how to get length of number in string? Python. Something quick. Yeah, something quick, like I want to get too much into this thing, like I want this to go fast. Length of string, let's find it. Python length, how to find, like how to get length of, how to get numbers inside a string. Yeah, I've done this very recently. I just wanna go fast. Yeah, we're gonna be doing this with ARI, regular expression as well. That sounds great. We can just remove this thing. Yep, so this is gonna be on code code. We're just gonna find all the numbers. Yeah, it's gonna be list, so num list for number in num list if str number bigger than, let's say, the 3 digits. No, 3 digits, 4 digits. Oh well, no, just give it the length, like num length. Yeah, better. Return true, and then return false otherwise. Right, so if string number bam 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 bam. Alright, so we should skip that one. Has turtle. Go and the other one was basically has big number. And with this being done, we should be able to keep moving forward. Yeah. Yeah. I'm scared of the kind of things that are gonna come. String number higher. Oh, we need to give it a length, sorry. I'm just gonna skip everything that has to do with requests as well. Yeah, whatever. Yeah. And we just skip this thing as well. And just imagine that we need to do this for every single programming language and all the libraries that come out. Yeah, this is gonna be kind of fun because no one's doing it apart from proprietary LLMs, OpenAI, Anthropic, all these kind of things. Yeah, why do we get this thing? Yeah, I don't know which other. Well, let's say has Google. Has Google Code. I'm just running this code. I'm just speed running this code because I just want to go for the fun, which basically is just get the LLM, evaluate things, and for real. $942. We're close to 1,000. Let's stop in here. Oh, we almost have 1,000. Yeah. So we have a lot of samples of code that work, that give an output that apparently we can use to make things work, to train this thing, to evaluate this thing, all that kind of stuff. So this is just for the code cleaning. This is kind of fun. So this is gonna be called data set or preprocessing. Data cleaning. Right. And we should just, wow, look at all these files, man. We should be able to, so from, yeah, just save all this code somewhere. Because we just need to run the code once. Once we have the output that is expected from the code, we don't need it anymore. We just need to be, yeah, just once. And then we have just this code, we just fire and go. And the next thing would be, the LLM is going to be tasked to generate the code, and we're going to see if it works. And there's going to be a lot of trouble because there's going to be a lot of code samples that are going to give a value. Yeah, it's gonna be like LLM is gonna generate something, the output is gonna be known, it's gonna compare something to known, it's not gonna work and all that kind of stuff. But let's get doing. So let's bring the LLM. This is just data preprocessing. Let's save the whole thing somewhere. So how to create pandas? Yeah, how do we save this thing, man? Pandas data frame from list. Yeah, we can make a dictionary and we can just save the whole thing together. Yoo-hoo! Like this. Yep, we're gonna just do that. So data dict equals bang data dict instructions equals plain code instructions. Okay, data prompt Then we have code. So we have instructions prompt, params code, and basically output. Right. The instructions prompt, params code, and output. That sounds great. Now we need to create a data frame. So this is gonna be this thing in here. df cleaned data leak and df punto sorry. Just gonna save it to CSV. Be easier. Well, Parquet. Let's be professional. Yeah. So this is gonna be cleaned data, and it's gonna be called the same file name. Rename. Copy. Paste. Oops. Paste. Parquet. Yeah. Clean data. Yeah, good. And we can just run it again. Oops, sorry. Oh, we didn't save the thing. Alright. This is gonna be huge. This is gonna be mad with all these commas and all that kind of stuff. This is not gonna work. Yeah, it's not gonna work. Is there a better way to do this? Not in Parquet. Like, can we... I just ran out of batteries. Alright guys, so we're gonna leave it here. This is basically data processing. We couldn't save it anywhere, but we're gonna work that. So basically I think we're gonna save this to some kind of pickle. We're gonna save that to pickle or something similar. We're gonna leave this streaming here. So thanks for watching. If you finish the whole thing, like, subscribe, all that kind of stuff. We're gonna be working with more data sets and on this AlphaCode for Python, I guess, in the upcoming videos. So it's likely there's gonna be another video for the wall training, and just we have a lot of preparation. We have 1,000 code outputs that have kind of been cleaned. There's a lot of noise in there. There's a lot of garbage because there's gonna be functions that output something that's sudden and all that kind of stuff. But we're gonna be using that to see what we can do about it, and that's gonna be great. That's how you fine tune. You know, yeah, it takes time. So thanks a lot. See you in the next one. Bye bye.